Now let's take a look at a new definition associated with this idea of increasing and decreasing sequences. Let's suppose that if discarding finitely many terms of a sequence from the beginning of the sequence produced a new sequence with a particular property, then we would say that the original sequence would have that property eventually. Okay, we're going to try to see what I mean by this, but let's pretend that I'm working with a sequence that maybe looks like the following. Maybe I have a sequence that goes 1, then 2, then 3, and then all of a sudden it goes 0, -1, -4, -10, and it just goes downward forever for the rest of time. Notice that I wouldn't be able to say that a sequence like that is decreasing, because I can see here that in the first several terms, the sequence goes up in value, not down. However, if I can discard finitely many terms, just kind of like erase them from the beginning of the sequence, and what's left over is a sequence that's decreasing, then I could say the sequence is eventually decreasing. The key here is that I have to be able to discard finitely many terms, and it's got to be from the beginning of the sequence. So let's take a look at how this would apply down here in example 2. I want to show that this sequence is eventually strictly decreasing. Eventually, it only goes down. Well, I can start to see here that if I was to write out some of the terms of this sequence, let's see, by plugging in a 1, I would get 10 to the first over 1 factorial. Now you may not be fully familiar with what a factorial is, but I'll go ahead and quickly define it over here on the side. Remember that n factorial is defined as n multiplied by the number right before n multiplied by the number right before that, and kind of continually multiplied all the way down until you hit the value of 1. So for example, something like 5 factorial would be written as 5 times 4 times 3 times 2 times 1. Right? I start at the number 5, and then I go down by 1 every time until I hit 1, and then I stop. So if I do 1 factorial, that's pretty boring. That's just going to be the number 1. So 10 to the first over 1 is going to be 10. Now, the next number that I get out of this sequence here is going to be 10 squared over 2 factorial. Notice that would be like 2 times 1. So the next number here is 50. If you calculated it out, the next number that you would get would be like 1,000 over 6. And that's actually bigger than 50. Very interestingly, if you look at this from the onset, it looks like these numbers go up. But again, the problem says eventually they start to only go down. Let's see how we could actually justify that. We'll use one of the 3 techniques that we talked about in the last video. Now, or the last several videos, I should say. But in order to determine which is best, we want to briefly think through what each approach is going to require. Would it be advantageous here to use calculus and take a derivative here? Well, probably not, because if I converted this to a matching function, I don't know how to take the derivative of a factorial. I didn't learn anything like that in a Calc 1 class. Doing a difference here is actually also not going to be very, very simple and straightforward. However, a ratio is going to be very useful, and ratios will often be very useful whenever factorials are involved. So let's go ahead and say that we will look at a ratio of consecutive terms. So I'm going to look at a sub n plus 1 over a sub n to see what happens. Notice the number in spot n plus 1 is going to look like 10 to the n plus 1 over n plus 1 factorial. And in the bottom, 10 to the n over n factorial. Now, to simplify this down, I can simply multiply by a reciprocal and try to clean this stuff up. So let's see what we have here. Now, the tens seem pretty easy, right? I have n plus 1 tens in the numerator, n tens in the denominator. That's just going to simplify down to a 10 in the numerator. But what about the rest of what I have? Notice that actually I can write out in detail what each of these different factorials are to see how they can cancel. n factorial is going to be n times n minus 1 times n minus 2 times on and on and on all the way down until I get to 3 times 2 times 1, however long that takes. I'm just writing out the general pattern of what that would have to look like. Notice in the denominator I can do the same thing, but my multiplication problem has to start at n plus 1. Well, what would come right before n plus 1? That would be n, and then n minus 1, and then n minus 2, and then I would just keep going and going and going until I hit 3 times 2 times 1. Well, if you look at that, most of the terms there are actually in common between the, or factors are in common between the top and the bottom. I have these n's and n minus 1s and n minus 2s, and really everything else down the line is going to be able to be canceled out. I'm just going to be left with this 10 over n plus 1. Now, again, with a ratio of consecutive terms, I'm curious if this is going to be greater than 1 or smaller than 1 or equal to 1 at different points in time. Specifically here, if I want to show that it's decreasing, I'd like to show that it happens to be smaller than 1. However, is this always smaller than 1 for all values of n? Well, no. I mean, like if n is a 1, it's certainly not going to be smaller than 1. I'm going to get 10 over 2, which is 5. But I can say that we see that 10 over n plus 1 will be less than 1, indicating strictly decreasing for values of n where? Well, notice if I pick values of n at 10 or higher, I can make the denominator always larger than the numerator. And so my a sub n plus 1 over my a sub m will be less than 1 for n values greater than or equal to 10. And thus, my a sub n plus 1 will be less than a sub n for all n greater than or equal to 10, which shows that a sub n is eventually strictly decreasing, right? This is showing me again that once you get past the spot of 9, when you get to spots 10 and on, and you start doing these ratios, you start doing A11 over A10, A12 over A11, you always get things that are less than 1. Notice, though, you can see that if n was the number 9, then this would come out exactly equal to 1, which means that a number 10 and a number 9, when divided, would have to equal 1 exactly, which actually makes a lot of sense here. You could even go ahead and write out in detail what a number 9 and a number 10 are and see that they actually are indeed the same value. This here, though, concludes the argument that we need for this particular question. We have shown that this is going to be an eventually strictly decreasing sequence.